MAP4C 7.1, the amount of an annuity. Previously, we learned about simple and compound interest, which is a lump sum investment for a period of time. So all of the money is deposited for the entire duration and then withdrawn at the end. The difference is an annuity is a series of equal payments made at regular intervals. In an ordinary simple annuity, payments are made at the end of each compounding period. So an amount of an ordinary simple annuity formula, we're going to first of all talk about the way that we are generating money. We are making regular deposits. Our total amount is made up of our regular payment that we're making times n, the number of compounding intervals, the number of times that we're going to actually make this payment. So the product of those two, the regular payment times the number of compounding periods, is the sum of the money that we've actually deposited. And it will also earn interest. So when this type of investment starts, there's very little money in the account to start because we haven't made a lot of regular payments. But let's define each of these variables. A is the total amount of the investment. R is the regular payment in dollars. I is the interest rate, and remember to adjust that for the calculation at the compounding interval, as well as N is the total number of compounding intervals. So you take your payment frequency per year and multiply that by the number of years. All right, so let's take a look at an example. Suppose $450 is deposited at the end of each quarter for 1.5 years in an investment account that earns 10% per year compounded quarterly. Determine the amount of the annuity in 1.5 years. So we know that this is an annuity because $450 is deposited regularly at the end of each quarter. So it's not all at once. And for that reason, the interest seems to be growing very slowly at first because there's very little money that's deposited in the account and earning interest. As each term goes by, more deposits are accumulating and therefore more interest is accumulating. Let's start using the guess method to solve this problem. What given information do we have? The regular payment of $450 is R, $450. I, the interest rate, is 10% as an annual percentage rate, but remember to adjust that so that we have the value at the compounding period. This is compounded quarterly, so therefore that's 4 times per year. When we're calculating interest, we'll use the value 0.025. Next, the number of compounding intervals or compounding periods is 4 times 1.5. 4 because we're compounding quarterly, that's 4 times per year, and this investment is going to be for 1.5 years. So that's 6 periods of calculating interest as well as making deposits. The part that's unknown is the amount of the annuity. So we'll use our formula, substitute in our values, and then evaluate. So we'll solve. Now, I'm illustrating this on a calculator. If you would like to do this all in one step, make sure that you follow these instructions. It might vary from calculator to calculator. What's important to remember is that a calculator does not necessarily understand that the operation multiplication is to happen between a number, like a coefficient here, and a bracket. So make sure that you include those operations if you're getting an error. Next, this exponent within the brackets, notice this is a nested bracket, so we're going to make sure that we're careful opening and closing brackets. This will affect the parentheses here for 1 plus the interest rate is affected by this exponent. So that being said, on my calculator I have x to the power y as the key for accessing an exponent. On your display it might look like the up arrow, or a caret is the name of that symbol. And then make sure that for division on a computer, in computer language that's a backslash, to make sure that it's including this entire numerator. When you hit equals, you get this value. Remember that we're talking about money. We're rounding to the nearest hundredth, or 2 decimal places, because cents are to the nearest hundredth. So I write a dot above the equal sign to show that I've rounded off to the nearest hundredth. So this is the amount that's in the account after 1.5 years. Next question asks, how much interest was earned in 1.5 years? So we have our amount, we have our regular deposit, the number of compounding periods, but we don't know our interest, how much interest was earned. So rearranging this formula for the amount, for I, subtracting Rn from both sides, we end up with the amount minus the sum of our regular payments. Remember, R times N, the regular payment times N, the number of times that we make that regular payment, that's all of our money. So the amount that's in the account, whatever's left over, the difference between the amount that's in the account and what we've contributed is what is interest. So the amount minus the regular payment times the number of times that we make it, we've actually contributed $2,700 of our own money, which leads us to the interest that we earned. The difference is $174.48. So we're going to investigate this through a spreadsheet to see the process. It'll maybe give a better understanding, or at least a different way to interpret the system of calculation for interest. The first quarter we have $0. We start off with $0, but at the end of that month, we're going to earn 0 interest on $0, but we have to make the deposit at the end of the month. That's what makes it an ordinary simple annuity. We have to have this timing of deposit at the end of the month in order, and calculation of interest at the end of the month in order to be an ordinary simple annuity and use that formula. So at the end of the first quarter, $450 is deposited. That'll be the starting balance of the next quarter. So now money is sitting in that account and earning interest during the second quarter. And 0.025 times 450 is $11.25, because it's just on this amount here that's deposited in the account. So altogether, we have our $450 at the beginning of the term. We've earned $11.25 in interest, and we also add our deposit for this second quarter right at the end. So $911.25. As we start the third quarter, it's the same as the ending balance of the second quarter. The interest earned, however, is calculated based on the amount that is deposited during that interval, and that is $22.78. Notice that that's a pretty significant increase from the previous interval because we've made 2 deposits of our own money at that point. So there's more money that's invested at this time, and that's why we're seeing such a rapid increase in interest, because the actual amount of money that we've invested into this account is larger. All right, so that being said, we make a deposit at the end of this interval, third quarter, and add this row, the starting balance, the interest that's earned, and the deposit to get our ending balance. This process continues until the end of 6 quarters, which is 1.5 years, as our problem was suggesting, and our balance is $2,874.48. So notice the sum of these deposits is the $2,700. Our total amount is here, and that difference is the sum of the interest.